Good afternoon. My name is Andrew Hughes. I'm a graduate student at East Carolina University in the Masters of Network Technology program, and this is my presentation on Zero Knowledge Proofs for Dr. Lunsford's ICTN 6875 course. During this presentation, I will be covering what Zero Knowledge Proofs are, examples to help understanding, the history behind Zero Knowledge Proofs, the minor relevance of them, two helpful journal articles, and a short bibliography of the presentation. So, what is a zero-knowledge proof? Well, a zero-knowledge proof is a method by which one party, the prover, can prove to another party, the verifier, that something is true, without revealing any information apart from the fact that this specific statement is true. So the prover is not giving away any information to the verifier other than the fact that they know what they should. During research in cryptography in the 1980s, the question was asked, what if the verifier is not trustworthy? One would not want to give them a password. Now, for any mathematically inclined persons out there, please note that a zero-knowledge proof is not technically a proof. A true mathematical proof must demonstrate that a statement is always true, and as we will find out soon enough, there is, mathematically speaking, a small chance that a verifier could cheat a zero-knowledge proof. Now, zero-knowledge proofs have certain requirements. These are completeness, soundness, and zero knowledge. The completeness requirement states that if the statement is true, the honest verifier will be convinced of this fact by an honest prover. The soundness requirement states that if the statement is false, no cheating prover can convince the honest verifier that it is true, except with some small probability. I talked about this in the last slide. This is the soundness error. The soundness error states that there is a small probability that a cheating prover will be able to convince the verifier of a false statement. There are, however, a lot of stipulations for this. Firstly, in most examples of the soundness error, the verifier is limited to sending only single-character messages to the cheating prover. This gives the cheating prover a 50% chance on the first try to guess correctly. But in the actual application of the protocol in cryptography, the zero-knowledge proof function is done multiple times and has a very large amount of characters that would basically make this impossible to guess. But math doesn't lie, and even if there is a small chance, then it still must be addressed. Well, finally back to the requirements. The last requirement is zero knowledge. This is of course where the name is derived from and states that if the statement is true, no verifier learns anything other than the fact that the statement is true. On to variants of zero knowledge. There are three variants of zero knowledge. These do not especially affect the world of cryptography yet, so I'm going to define them for the sake of completeness and move on. Firstly, there are perfect zero knowledge proofs. This happens if the distributions produced by the simulator and the proof protocol are distributed the same. Secondly, there are statistical zero knowledge proofs. These happen if the distributions are not necessarily exactly the same, but they are statistically close, meaning that their statistical difference is a negligible function. And lastly, there are computational zero-knowledge proofs, if no efficient algorithm can distinguish between the two distributions. Now, for an example to make all of this information a little more clear. Think about the prover and the verifier from earlier. In this common example, we have Alice as the prover and Bob as the verifier. Now let's say that Bob wants to send Alice a confidential message full of trade secrets or something of the like. He needs to verify that Alice is who she says she is. He needs Alice's secret key to prove this. But Alice doesn't know Bob. She doesn't want to send her secret key to someone she doesn't trust. What do we do? Well, Bob is going to send Alice a message, and he's going to encrypt it with Alice's public key. Bob knows that without Alice's secret key, he will not get the proper reply to his message. This message could be anything. The point is that without Alice's secret key, she cannot decrypt the message and verify that she is in fact legitimate. So Alice does decrypt the message and sends it back to Bob. This way, Bob gets his verification, and Alice doesn't have to send her secret key to anyone. This is the difference between zero-knowledge protocols and other cryptographic protocols. The secret key never leaves and can therefore not be intercepted. Now for a little history. While zero-knowledge proofs are an emergent technology due to their application with blockchains, they are by no means new. They were in fact thought up in 1985 by three MIT researchers by the names of Shafi Goldwasser, Silvio Micali, and Charles Rakoff. In their paper, The Knowledge Complexity of Interactive Proofs, they came up with the idea of knowledge complexity. Knowledge complexity is a measurement of the amount of knowledge about the proof transferred from the prover to the verifier. They asked, what if you can't trust the verifier? Fast forwarding to present day, modern relevance of zero-knowledge proofs are Secure Remote Password Protocol, or SRP, and the introduction of zero-knowledge proofs to blockchain security. SRP is a form of Password Authenticated Key Agreement Protocol, also known as PAKE. PAKE is an interactive method for two or more parties to establish cryptographic keys based on one or more parties' knowledge of a password. Now, SRP is an augmented form of PAKE. Augmented, meaning in a client-server scenario, the server does not store the password data, so a compromised server cannot masquerade as the client unless they first perform a brute force search for passwords. SRP is used in a wide variety of protocols and programs, most notably for strong password authentication in EAP, SAML, and SSL and TSL. This is because the protocol has a multitude of desirable properties. Like all PAKE protocols, it is resistant to man-in-the-middle attacks due to the fact that they would not be able to obtain enough information without further interactions with the parties for each guess. It is also resistant to dictionary attacks. This is because in the most up-to-date version, version 6, only one password can be guessed per connection attempt. This protocol also does not require a trusted third party, such as Kerberos, because it is zero knowledge. Now, on to the most recent examples of modern relevance, zero-knowledge proofs in blockchain technology. For those of you who don't know, blockchains are cryptocurrency. The most notable examples would be Bitcoin or Ethereum. Now, most of these blockchains were designed with transparency in mind. Information such as sender, recipient, addresses, and amounts are all publicly viewable. That lack of security is changing, and there is becoming a need for more security. Banking regulatory requirements are starting to require privacy and security of the users. Large companies such as JP Morgan and ING, who use Ethereum and a new Zcash blockchain, use a new security measure called ZK SNARKs. ZK SNARK stands for Succinct, Non-Interactive Arguments of Knowledge. Succinct meaning the size of the messages are tiny in comparison to the length of the actual computation. Non-interactive means that there is little or no interaction between the prover and the verifier, with only a single message being sent between the two. This also has a public verifier property that means anyone can verify the blockchain without renewed interaction. Argument means the verifier is only protected against computationally limited provers. Provers with enough computational power can create proofs/arguments about wrong statements. Note that with enough computational power, any public key encryption can be broken. This is also called computational soundness, as opposed to perfect soundness. And lastly, of knowledge. It is not possible for the prover to construct a proof/argument without knowing a certain so-called witness. For example, the address he or she wants to spend from, the preimage of a hash function, or the path of a certain Merkle tree node. For this presentation, I have used two journal articles that have helped me to understand and explore new avenues of approach for zero-knowledge proofs. These are A Survey of Zero-Knowledge Proof for Authentication by Jitendra Kurmi and Ankur Sodhi, which was published in the International Journal of Advanced Research in Computer Science and Software Engineering, and Authentication Based on Non-Interactive Zero-Knowledge Proofs for the Internet of Things by Francisco Marin Fernandez, Pino Caballero Gil, and Candido Caballero Gil, which was published in Censor's Journal. The first journal, Survey of Zero-Knowledge Proof for Authentication, was extremely useful. It was easy to read and understand and explained the different algorithm variations of zero-knowledge authentication protocols such as public key encryption, peer-to-peer identity authentication, RFID applications of zero-knowledge proof authentication, and a proposed zero-knowledge proof based on Diffie-Hellman key exchange. Now, the first authentication protocol that the journal explains is the simplest and provides only one-way authentication. In this process, only the server can authenticate a client. The advantages of this authentication is that the password does not travel over the wire, keeping a man in the middle out of the loop and away from doing any kind of damage. In this process, the password is stored on the server in encrypted form, making it even less vulnerable to attacks. This protocol also makes use of nonces at each step to add yet another layer of security. The second authentication, the journal explains, is public key encryption and zero-knowledge password authentication. With this authentication, the server and client can verify each other, enabling two-way authentication, unlike in the previously stated protocol. This protocol also makes use of nonces at each step. On the first step, the user sends his username and nonce to the server after encrypting it with the server's public key. Next, the server will decrypt the message with the user's private key and learns the value of the sent nonce. The server will then generate its own nonce and a random session key for the user and send the encrypted data to the user. After receiving this encrypted data, the user will decrypt it with his private key and learn the values for verification. Using these values, the user sends them encrypted back to the server. The server decrypts this message, and if the value is as expected, is allowed access. The third authentication the journal explains is the peer-to-peer authentication based on zero-knowledge proofs. This authentication includes two phases, a pre-processing phase before authentication, where each node will go to a management center for registration, and the management center will give each node a different unique identifier, and an identity authentication phase where the nodes are identified using the zero-knowledge proof identification system. During the second phase, the management system is not being used. The way the system works is the prover sends the verifier the unique identifier and their public key, and the verifier matches this to a one-to-one function. If it all adds up, then the prover continues. If it doesn't, then the prover is a fraud and access is denied. This journal also explains the Diffie-Hellman key exchange in more technical terms, but it is like my example at the beginning of the presentation. The author uses the same names, Alice and Bob, as the verifier and prover. Alice proves to Bob that she is legitimate by generating a secret key for the session and sending it to Bob. Bob will match the encrypted information and verify Alice. The final authentication protocol this journal explains is the mobile RFID application. Like the peer-to-peer authentication, this also uses two phases. In the first registration phase, all tags and readers are registered with the central server. The reader will receive a username and password. In the second authentication phase, the journal explains how the tags will be verified. First, the reader queries the tag and sends its specific information to the tag. Next, the tag computes an algorithm and sends it back to the reader. The reader sends this algorithm to the server, and the server checks its database for the stored hash function of the tag. If it's a match, then access is accepted. If not, then it's denied. The second journal, Authentication Based on Non-Interactive Zero-Knowledge Proofs for the Internet of Things, combined two emerging technologies and gave in-depth examples of them. This journal talked about mobile ad hoc networks, vehicular ad hoc networks, and sensor networks involving zero-knowledge proof authentication, and the problem that can arise with key management. It also showed Android's current implementation of zero-knowledge proof authentication. Mobile ad hoc networks, or MANETs, prove to be a problem when it comes to node security, as the nodes do not have access to the internet for verification on a server. These nodes can jump off of other nodes that have internet connection. Using zero-knowledge authentication, these nodes can verify themselves to legitimate internet characters and still remain secure. For vehicular ad hoc networks, or VANETs, the goal is to obtain better traffic management and prevent vehicular mishaps. In some instances, it is best to send information encrypted, and the use of zero knowledge is best in this situation because it is lightweight. Finally, this journal explains the application of zero knowledge proof for wireless sensor networks. The problem with wireless sensor networks is that they are becoming increasingly easier to create, using such platforms as Raspberry Pi, Odroid, and Arduino. Mostly, sensor networks do not use any security for their broadcast, and zero knowledge would add a layer of lightweight and strong authentication. This journal explains zero knowledge proofs very effectively if you ever plan to begin your research with this particular journal. In conclusion, I have my bibliography page. I researched all of this presentation off of journal articles, magazine articles on the World Wide Web. These articles are as shown. Thank you for listening, and I hope you have enjoyed my presentation. Good evening.